Okay, good afternoon. Welcome. So we will do our operating systems lectures together. So this is CS-342 operating systems course, a third-year course in Bilkent University. So we will do this course together. And what this course will do is it will teach you the operating systems, the concepts related to operating systems, and the operating system components. While doing that, we will also have projects and programming homeworks. So in this way, you will have a hands-on approach. So at the end, you will have also a practical experience. You will do lots of programmings. And as a result, you will learn how operating systems are implemented and how they are used and how we can do low-level programming with operating systems and so on. In this course, you will see examples from real operating systems. Especially, we will cover Linux and how it is designed, how the components of that is designed, and what are the important design decisions and so on. We will also touch to some other operating systems like Windows and so on. And as I said, the course will involve lots of programming. So the programming will be done using the C programming language. So we assume that you know C already because you have taken the C++ course, CS-201 and CS-202. So the course will be three sections. Sections 1 and 2 will be taught by me, and section 3 will be taught by William Sawyer. And this is the course weekly schedule. So you are section 1 students. So we will meet on Tuesdays and Thursdays. On Tuesdays we will meet at 1:40 p.m. and on Thursdays we will meet at 3:40 p.m. And we have a course page set up, and you should visit this page quite frequently, okay? And there we will post some announcements, and you will follow the announcements. And about the projects, especially, we will post lots of announcements that will direct you how to do the project and so on. We will post some new material whenever required. So you should follow the announcements quite frequently, all right? And this is our course textbook, okay? So we will cover operating system concepts, the 7th edition by Ibrahim and this is our textbook. Everybody should get this book and should start reading. Actually, this textbook has a new edition, but we could not get it, so it will be available around April. So therefore, we will not be able to cover the new edition, which is the 8th edition. Okay, so that edition will be covered next year. This year, we will cover the 7th edition. So you can get it from the bookstore. If the bookstore does not have it, you can get the book from the previous year students. For that, we have established a forum where you can ask students, for example, if they are willing to sell their books and so on. Okay, so you can go to the forum and post a message indicating that you would like to buy a book and so on. So I also give this address to previous year students who wish to sell the book. So you can buy the book from them as well, if you wish. So the recommended text, we will also cover some topics from Modern Operating Systems by Andre Tannenbaum. You don't have to buy that book, but some material that is covered in the course may be included from this book. Okay, so what is the plan for the course? So it will span 14 weeks. So in this course, we will start with Introduction to Operating Systems in the first week. And then, starting next week, we will start with the basic operating system concepts. The one major operating system concept is the processes and threads. We will start covering them in the next week. Okay, so that means this is the third chapter next week. So the first week, this week, we will cover chapter 1 and 2 from the textbook. So therefore, you should start reading those chapters as soon as possible. So then next week, on Tuesday, we will start covering chapter 3, which is processes and threads, okay? And then we will cover CPU scheduling, then we will cover synchronization problem, how we can solve the synchronization problem among the processes and so on. Then we will cover deadlocks, then we will cover the main memory management and other major operating system functionality. We will see virtual memory, what is the role of the operating system in virtual memory implementation and so on. Then we will see the file concept, how the file concept is provided by the operating system. So we will see the file systems providing this concept. We will see the mass storage structure and management, how the disk blocks are allocated to files and so on. Then we will see the input-output, how the I/O devices in the computer are managed and controlled by the operating system. Then we will see some protection issues, and if we we will briefly cover distributed systems at the end. So this is the basic outline. So this is posted on the website as well. So as I said earlier, the course will have programming projects, and projects are very important in order to have a full understanding of the operating systems. Okay, just understanding the concepts is not enough, but to appreciate the issues involved in operating system design, you should be doing also projects. So there will be around 5-6 projects. Okay, those projects will involve low-level programming in the Linux environment. Some projects may include kernel-level projects. You will touch to the Linux kernel, and after you develop your project, you will submit it through the website, and we will compile your projects and test them using some automated tools, and you will get your grades depending on the results that are produced by your programs. We will also examine, of course, your program source code, and all the projects and homeworks will be developed using the C programming language. Therefore, we suggest you to start refreshing your C and C++ knowledge immediately. We highly recommend you to get the following book. Okay, it is the C programming language book written by the inventors of the book, Kernighan and Ritchie. So it's a very good book. So it's a must-have book for serious C programmers. So we suggest you to buy that book and start reading that. So I suggest you to spend this week and next week to refresh your C++ and C knowledge and skills. Okay. All right, so since the projects will be done in the Linux environment, you need to install Linux on your desktop and laptop computer. Of course, you can use also the BCC machines where Linux is already installed, but it's also good to have your own Linux system so that you can work on that at any time, okay? So you don't have to come to school to work on Linux and so on. So we suggest you to install Linux on your desktop computer. You can install Ubuntu, for example, as the distribution, version 8.10. And we will provide some links how to install Linux and so on the course website, okay? So your first homework will be actually about the installation of the Linux. So it will ask you to install Linux on your computer and make it working, okay? This will be your first homework, which will be posted this week. So we will announce when we post the homework to the website, okay? It's very important that everybody can program in C and in Linux, okay? So in order to, in this course, this is very important. So at the end, you need to perform above a threshold, okay, in the projects to pass the course, okay? This is the requirement. You have to be above a threshold which will be determined at the end of the course, okay? So you have to be above that threshold to pass the course. So other issues about the course, we encourage you to ask questions, okay, in the class and in the office hours, to me, to TAs and so on. And also we suggest you to discuss the topics if you did not learn them completely among yourselves. Please ask questions, okay? And another issue is the attendance is important. You should come to the lectures and you should ask the questions in those lectures. And we recommend you to use the forum. If you have, for example, a debugging problem in your program, okay, you cannot debug an error, you can post a message there. Hopefully some student has managed to solve that problem. He or she can reply. So we are encouraging you to use the forum, okay? And you are suggested to help each other to debug the programs, okay? If you hit an error while doing a C programming, okay, and if you spend some time and still could not pass that error, please ask to your friend, okay, or to some other people to pass that error, okay? You should definitely pass that error in order to move, okay? And therefore, we encourage you to help each other while debugging the programs, okay? So this is important. And please be persistent in debugging, okay? Now, don't give up, okay? Sooner or later, you will pass those errors. You will solve those errors, okay? But you should be persistent. It may take for you 10 minutes, 1 hour, 2 hours, 3 hours to pass an error, but when you managed to solve that error, okay, then next errors, similar errors, will be solved by you in a few seconds, okay? So it's important that you should be persistent in debugging and make sure that you actually learn and develop skills to debug the programs. All right, so what about me? My name is Ibrahim Korpeoglu. And you can obtain detailed information about my work and so on from my website, but I will introduce myself very briefly. I'm an assistant professor in the Department of Computer Engineering of Bilkent University. I received my BS degree, undergraduate degree, from the same department, Bilkent University Department of Computer Engineering, where you are now. And I received MS and PhD degrees from University of Maryland College Park, and my PhD thesis was on mobile and wireless networking. And I also have some industry experience in some companies like Ericsson, IBM, Bell Labs, and Telcordia, which was formerly Bellcore. And in those companies, I worked on networking systems, protocols, and algorithms. Here, I usually teach the operating systems course, and I also teach wireless networking courses. This is my current teaching activity. And in the past, I have taught courses on data structures, digital design, and network programming. And I do research on computer networks, and especially on wireless and mobile networks, on sensor networks, mesh networks, peer-to-peer networks, and on some networking technologies like Wi-Fi, wireless LAN technologies that we use every day, and WiMAX, Bluetooth, Zigbee, wireless technologies. And I am also interested in doing research in distributed systems, algorithms, and protocols. So about the format of the lecture. So all the lectures will start at some hour 40, okay? Today it will start at 1:40 p.m. And on Thursday it will start at 3:40 p.m. Please be on time. And the lecture will be 45 minutes long, okay? So the last 5 minutes, I will try to leave that last 5 minutes for asking questions and finishing that 1 hour lecture. Of course, you can ask questions at any time during the lecture, okay? Don't hesitate to ask questions. Then we will have a break, 10 minutes break. You can get a coffee and tea to refresh yourself during this time, and then we will start the next lecture, okay? So this will be the format of our lectures. Any questions so far? Okay, so now we can start with the introduction to operating systems, okay? So this will be our first lecture. It will be an introductory lecture. Here we will try to give you the basic operating system definition and so on. So in this lecture, in this first lecture, introductory lecture, what we will try to give you is, first we will try to explain what an operating system is doing, okay? What an operating system does. What is an operating system? An operating system is system software that is closely related with computer hardware. So in order to understand how the OS is working and so on, you should understand also the computer hardware, okay? So we will briefly touch to computer hardware design and how the system is organized, computer system hardware is organized, over which the operating systems are running. And then we will briefly describe the general operating system structure and operations. And also we will describe briefly the major operating system concepts and components and functionalities. Those include the process management, memory management, storage management, protection and security, input, output, and so on, okay? Then we will talk about the computing environments where the operating systems are run, the operating system functionality is needed, and so on, okay? And we will close the first chapter in this way. So let's start with what an operating system is, okay? So the objective of this first lecture is to provide a grand tour of the major operating system components, okay? We will just briefly describe them, the major operating system components, and then we will provide a coverage of the basic computer system organization. The detailed information about that is actually obtained in your CS-342 course last year, okay? So we will briefly summarize the computer organization, the topics that you have learned in CS-342 last year. So what is an operating system? So you may have developed an idea about that so far because you use Windows, Linux, and so on, right? So it's a software that you must have in your computer in order to use the computer, okay? So you cannot use the bare hardware without an operating system to run applications, to develop programs, and so on, okay? All the computers that you are using have an operating system. Of course, the type of operating system depends on the computer that you have. The operating system for a cell phone, for example, is different from the operating system that a PC has, but all those systems that can be used conveniently by the users have an operating system. So what is an operating system then? It's a program, okay, it's a software, piece of software that acts as an intermediary, a middleware software between a user of a computer, between the users like us, and the computer hardware, okay? So it acts as an intermediary, all right, between the users, the applications and the users, and the computer hardware. So the goal of that system is, the goal of the operating system is the following. It helps you to execute user programs and makes solving user program problems easier, okay? With the operating system, it is easier to use the computer. It is very difficult to use the computer if you do not have an operating system, okay? You never tried that. And therefore, the operating system is a software that makes the computer system, the hardware, convenient to use, okay? With that, hardware becomes friendly, okay? Becomes easy to use and so on. After you install Windows or Linux to your hardware, okay, then it becomes a nice device over which you can run applications and so on. Without operating system, you don't know what you should do, okay? So it provides you a convenient environment to run applications and to program new applications and so on. Another goal of an operating system is utilizing the computer hardware, using the computer hardware in an efficient manner. Nowadays, in your computer, you run several applications, several processes at the same time, all competing for resource and so on. It is the operating system is actually that is managing the resources and enabling lots of applications to be run in the same computer without any problem. So nowadays, actually, several users can log into the same system and use that system without any problem. And this is enabled by the operating system. Without operating system, this cannot be done, okay? So the operating system manages the computer hardware as well and uses the computer hardware in an efficient manner, manages the resources and so on. So if we look to a general computer system, a computer that you have and you, okay, it's a computer system, okay? So what are the components of that, the general components? So if you look to a general system, then those are the components. The hardware, the keyboard, the machine, the monitor, and so on, the mouse, and so on. This is the hardware, okay, which has inside the machine, we have the CPU, memory, input-output devices, and cards, and so on, okay? So this is the hardware, and this hardware provides the computing resources. The CPU enables you to execute instructions and so on. The memory enables you to store some data variables and so on. The hard disk enables to store your files and so on. So hard disk, memory, CPU are the basic resources, okay? Basic computing resources. The computation is happening actually there. The CPU is actually doing the computation. So this is one component, the hardware of a computer system. The other component of a computer system is the operating system, okay? So it is actually the system, software, that controls and coordinates the use of hardware among various applications and users that can use the same system concurrently at the same time, okay? So the operating system controls and coordinates the use of the hardware, okay? So it is the second component, and as the third component, we have the application programs, okay? So they are actually the useful programs that you use to do something. So those application programs define the ways in which the system resources are used, the system resource, the hardware and so on are used to solve the computing problems of the users, okay? So if you need word processing, then you open, for example, a word processor. If you need some calculation, you open an Excel or spreadsheet, okay? So these are the applications and that run over the operating system and get the help of the operating system to access and utilize the hardware to solve the problems that you would like to solve actually, okay? So word processors, compilers, web browsers, database systems, video games, and so on are all the application programs. This is the third component that a computer system usually has. And the fourth component that a computer system usually has is the users, okay? So the students are the users. of a computer system can be the users of a computer system, or some other machines can be the users of one computer. Okay, so nowadays networking enables other machines to contact to a computer and use the services that are running in a computer. So those other machines can be actually the users of a machine or of a system. Okay, so these are the four basic components of a computer system, and the relationship of those components are seen in this figure. So at the bottom, what we have the computer hardware, right? So how that hardware is organized, you have seen in the last year in CS-224 course and also in CS-223 course, right? And on top of that, we should have an operating system, which makes the hardware more user-friendly and which manages the hardware, okay? So with the operating system here, we have a nice environment over which we can run programs. Without the operating system, it is not easy to run programs directly on the hardware, to develop applications and so on, okay? After you install the operating system, it becomes easier and so on. So we have the operating system on top of the hardware. After we install that, which is always up and running, the operating system and the power is on the computer, then we can run other applications. Those applications can be classified as user applications or system applications, okay? System programs or application programs. So system programs can be, for example, the compilers, assemblers, text editors, and so on. They can be classified as the system programs. And the application programs can be, for example, the database systems, the web browsers, or, for example, the word processors, the spreadsheets, and so on that you use can be the application programs. Whether it's a system program or application program, doesn't matter, okay? They are the processes or applications, they are programs that are running on top of the operating system and utilizing the operating system to use the hardware, okay? They cannot directly access the hardware. They are actually calling some operating system routine or function to access the hardware. The hardware knows the details, the operating system knows the details of the hardware, and all the applications are accessing the hardware via the operating system, okay? They call a function of the operating system. So on top of the figure, we have the users that are actually running those applications, that are creating those processes, running those applications, and so on, to get something done in the computer, okay? So this is the general structure of a computer system, and these are the four basic components of a computer system. So in this course, we will focus on the operating system, okay, how it is designed, what are the issues are here, what is the role of the operating system, what is the job of the operating system, what are the concepts provided by that, and so on. This will be the topic of this course. So in the last year, you have seen how the computer hardware is designed, right? And in, for example, in some of the courses this term, like the database course, you see, for example, how some of the processes here, like the database systems, are designed and so on, okay, that are running on top of the operating system. The database systems are actually utilizing the services of the operating system to access the hardware, to access the files, the hard disk, and so on, okay? So if we now define the operating system, what is that? So the operating system is actually a resource allocator. That means all the resources in the computer, hardware or software resources. For example, the printer, the keyboard, the hard disk are the hardware resource, but the files are software resources. All these are managed by the operating system, okay? The operating system, for example, decides who should use which resource and so on. Also, it resolves the conflicts. If several processes or applications that are running concurrently in the system, if those several processes make some conflicting requests for a resource, then operating system decides between those conflicting requests for efficient and fair resource use, okay? So then you can visualize or consider an operating system as a resource allocator and manager, okay? The resources are allocated by the operating system to the programs and managed by the operating system, okay? And also operating system can be considered also as a control program. What is that? It controls the execution of the programs, okay, so that the programs are not harming each other, are not interfering each other. The modern systems that we have today, all the PCs that you have, laptops that you have, and so on, they can run several applications at the same time in the system, right? Several applications can be started. They are running concurrently, but they are sharing a single CPU most of the time, a single memory, RAM most of the time, okay? How this single hardware device component, CPU or memory, is shared in a proper manner among various processes that are running in the computer at the same time. It is handled by the operating system. Operating system makes sure that those processes are not interfering with each other while sharing CPU, memory, and so on. So that, for example, a process is not overwriting the memory area allocated to some other process. Otherwise, everything will be a mess, okay? The results will not be correct and so on. So also the input-output devices like keyboard, mouse, hard disk, and so on. We have lots of input-output devices, the screen and so on. They are all accessed via the operating system, okay? Operating system actually has the code, all right, low-level code that knows how to access those devices, okay? The application programs that we are writing, developing, and running do not know how to, for example, access the keyboard directly. What do? The application programs are usually actually calling just a function to do I/O, right? For example, in C, you just call printf to print something to the screen. This is just a function. But finally, it triggers when, after you call printf in your function, in your program, when the program is executed, okay? While it's executing, when it hits the printf function, when it starts executing that function, finally this triggers some operating system routine to run in the CPU to do the actual I/O to the video card, to send something to the video card, which will finally go to the screen, okay? To the grid, all right? So in this way, all the input-output devices are accessed via the operating system, and the input-output is done with the help of the operating system, okay? So therefore, OS is a control program that is controlling the input-output and so on, which program should do now, input-output, and so on, okay? So there is no universally accepted definition for an operating system, actually. So sometimes we can consider as an operating system the CD that we buy, okay? For example, for Windows, you buy a Windows CD, okay? So then the content of that CD can be considered as the operating system. You can say that, okay, I bought operating system CD, okay? So this is the operating system. But that CD actually contains lots of programs, all right? Hundreds, thousands of programs, okay, is contained in that, all right? So this course is not teaching how all these programs are written. This course is about a special program there in that CD, which is called the kernel, okay? So there is one program, okay, which is called kernel, that has to run all the time in the computer, okay, which is actually the operating system, okay? So inside that CD, you have one executable, which is the kernel, which is called kernel, okay, which is actually the operating system that we are talking in this course. This implements all the functionality that we will be talking in this course, like the process concept, file concept, and so on, okay? So you have usually in that CD lots of other programs, application programs, system utilities, system programs, and so on. But there is one piece of software called kernel, which is the most important in this CD, which is actually the operating system, okay? So we will see in this course how that is designed, okay? So the one program running all the time in the computer is the kernel. Everything else is either a system program or an application program that you can also install after installing the kernel and to the system. So what we see at the end is when you power on your computer, okay, on top of the hardware, when you power on your computer, the kernel operating system is loaded, okay, and ready to execute in memory. And over that, you can run system or application programs, all right? You can start some other applications like Word, Excel, and so on, which is actually using the services of OS to do some I/O and so on, okay? So the kernel, the operating system, is up and running all the time in the computer. It is not running all the time, but it is loaded into memory when you power on your computer. It is run in the CPU whenever required, okay? Whenever the running application in the CPU requires a service, or whenever an interrupt happens, and so on, okay? So how that kernel is loaded, so when you power on your computer, okay, we have a bootstrap program loaded automatically and run. All right, that bootstrap program is typically stored in ROM, read-only memory of the computer. It is installed there at the factory manufacturing time. Okay, so at manufacturing time of the computer, it is stored there. So when you power on your computer, this is the first program. That's a small program that is run. Okay, that program is sitting in the ROM. So it's also called firmware. So what it does is it initializes all aspects of the system, and then it starts loading the operating system, the kernel. Okay, I will use the term operating system and kernel to mean the same thing. Okay, the piece of software in the CD that is the most important, a single executable that has to be loaded in the beginning when you power on your computer, and that has to be sitting in the memory all the time and will run from time to time on the CPU whenever required. Okay, so that bootstrap program will load the operating system, the kernel. It will take the kernel from the hard disk and will put it into memory. Okay, this is loading. Okay, and then it will start executing that. Now the kernel will run and it will provide the GUI. For example, in Windows, it will provide the desktop, or in Linux, it will provide you the windows in which you can type your commands and so on. Okay, so it will provide that GUI where you can type your commands or where you can double click on icons. So after that, it has finished. Okay, now the system waits for your commands. You can type your command or program name, hit the return key and execute that command or program, or you can double click on an icon to run another program and so on. Okay, in a desktop environment. So in this way, you can start other applications and so on. When those applications are running now in the CPU, okay, they may request some service from the OS, and during this time, OS routines will be running in the CPU for a while, and then again the applications will run in the CPU and so on. So the hardware is shared by the applications that we can run and also by the kernel. Okay, so the CPU is running sometimes the application code, your Java programs, or C++ programs, and sometimes also the kernel code. Okay, whenever required. So we have a single CPU where the kernel code and application code can be run. Okay. So in order to understand the operating systems, we should have a general knowledge about the computer organization. Okay, so this is the knowledge that you acquired actually in CS-342 course. Okay, so we will briefly touch to some important issues here. By the way, do you have any questions so far? Okay, so we have obtained detailed knowledge in CS-342, but we will briefly describe the computer operation, hardware operation, so that we can understand the operating systems better. So what do we have as the hardware, as the computer, without considering the applications and operating system? What we have is, in a computer, we have a CPU, one or more CPUs nowadays. We have memory, and we have some devices, like the hard disk, like the keyboard, printer, monitor, and so on, network card, and so on. And for each device, which can be a mechanical device, for example, a keyboard, or a printer, or a hard disk, okay, for each device, okay, we also have a device controller. Okay, a device controller is a chip that controls the device, that knows how to deal with the device, how to talk to the device. Okay, so the CPU can interact with the device controller here, but not with the device directly. Okay, so the CPU can, for example, write some value to some register in the device controller, but it cannot directly interact with the device. Okay, so the controller itself is able to directly interact with the device. Okay, so what do we have in those controllers? In those controllers are capable of processing. So that processing, for example, they can execute some code in a special purpose processor here, or they can be designed, the hardware can be designed in such a way that it is able to do some functionality. Okay, so basically those controllers have some processing capability and also have some amount of memory, which we call as the buffer of the controller, local buffer. Okay, so at the end, when the computer is operating, when you power on your computer, what happens is that you have the CPU that is capable of running instructions. So this is the general purpose processor, and we have also the controllers that are also capable of doing something independent of the CPU. So what we have at the end is we have one or more CPUs in the system, device controllers connected together, all right, via a common bus to the memory. And the CPUs and the devices competing for memory, all right, they can try to access the memory, and also they are running concurrently. So I/O devices and the CPU can execute concurrently, meaning that while the CPU is executing some instructions of an application, of the program that you have written and running, while the CPU is running some instructions, the other I/O controllers can do something with the respective I/O devices. For example, the disk controller may try to retrieve some amount of data from the disk, which can take, for example, a few milliseconds, maybe 30 milliseconds. Okay? While the disk controller is busy with that, okay, in parallel, at the same time, the CPU may be running some application code. Okay? So therefore, we say the I/O devices and the CPU can execute concurrently, okay, through parallelism here. Each device controller is in charge of a particular device type. So here, for each device type, here we have a separate controller. And each device controller has a local buffer, as I said, a small amount of memory. It depends to the controller, to the device, how much buffer we have, okay? In some, for some devices, like for example, a serial port controller, we have a very small amount of memory, like 16 bytes, okay? But for the hard disk controller, we can have memory in the order of kilobytes, okay? And CPU moves data from the main memory to local buffers, okay? The CPU, if there is a data to be moved from the memory to the controller buffer, the CPU can do that, okay? So the CPU can move the data from here to there, or from here to there, okay? Because CPU can access the memory here and also the memory there, okay? This is the main memory. CPU can access both. So CPU has instructions, like move instruction or in-out instructions, machine instructions, that can be used to access the registers, buffers there, and also the memory cells there, memory words there, okay? So CPU can move the data from main memory to local buffer or vice versa. And input-output is done from the device to local buffer of the controller. So if you would like to do input-output, the input-output is done from the device first to the local buffer of the corresponding controller. For example, if you would like to retrieve a block of disk, okay, the block content is first retrieved from the spinning hard disk into the controller, and then it's retrieved from here to the memory, so that it can become available to the application that has requested data, okay? For example, an application that is reading a file. If you would like, for example, to send something to the printer, the data first goes from the memory to the printer controller, and then from the printer controller to the printer itself, okay? So the printer controller knows how to send that data in its buffer to the printer itself, okay? And the movement of data from the memory to the printer controller, however, is done by the CPU, can be done by the CPU, okay? So device controller, when, for example, the device controller is doing I/O, okay, with the respective device, and when that I/O is finished, okay, there might be an application here that is waiting for that I/O to become available, or that is waiting, for example, that the I/O operation has finished, okay, that is waiting for an event indicating that the operation has finished. Therefore, the device controller informs the CPU that the operation is finished. How? By causing an interrupt. So these device controllers can send interrupts, physical interrupts to the CPU, okay, when the operation, the I/O operation with the respective device is completed. For example, if the disk has retrieved a block from the disk, this controller has retrieved a block from the disk and the block is ready in this controller, then it can interrupt the CPU, indicating that now the data is available in the controller. Please take it. Then the CPU can run a special OS routine, driver routine, to retrieve the block of data from here to there, okay? Or, for example, when printer controller had data, okay, to be sent to the printer, printer is a very slow device. It is sending the data. During this time, the buffer is initially full. So the application that would like to send printer data cannot send the whole file to the printer immediately. It is sent piece by piece to the controller, okay, because the controller has a limited buffer. So when that buffer is written to the printer completely, the buffer becomes empty, okay? So then this can generate an interrupt indicating to the CPU, now the printer buffer is empty. Please send some more data from memory to there that can be printed, okay? So therefore, when an I/O operation is finished, a write operation to the device, or a read operation from the device, a write operation to device, or a read operation from the device is finished, the device controller informs the CPU about that by sending an interrupt, okay? So this is actually something that you should have already seen in the CS-342 course, but this is a review. So then what happens when an interrupt happens? So the interrupt transfers the control to the interrupt service routine. All right, so at the time the interrupt has arrived to the CPU, okay, the CPU might be running at that time an application code, a program might be running when a device interrupts the CPU. So what happens then? That program is suspended, okay, stopped for a while, suspended, and the address of the interrupt service routine in the kernel, which can serve the interrupt, is found from a table called interrupt vector, okay? So every interrupt has a number. That number is used as an index to that table, interrupt vector. And there we find the address of the special routine that is part of the kernel operating system that will handle the interrupt, okay? It contains the address of the interrupt service routine. Then that routine is run in the CPU. So when interrupt happens, the current running application is suspended, stopped. The address of the routine to be executed in kernel, and kernel is already loaded into memory, right? So the function to be executed, interrupt handler, is in the memory. So address of that is found via the help of the interrupt service, interrupt vector, and that function is now executed in the CPU. The address is loaded into the program counter in the CPU, and that function, interrupt service routine, is run in the CPU to handle the interrupt. And handling the interrupt may be something like this: moving the data from here to there, for example, or moving some more data from the memory to the controller buffer, and so on, okay? In this way, you handle the interrupt. You do whatever is required when you receive an interrupt. And after you finished handling the interrupt, what you do? You again give the CPU to the application that was suspended, okay? So that the application can continue from where it is stopped, okay? Okay, when you, of course, when you actually save the address, when you stop the application to execute an interrupt service routine, you have to save the address of the interrupted instruction in the currently executed program, okay? And also you have to disable the incoming interrupts while another interrupt is being processed to prevent a lost interrupt, and so on. So these are the things that you should be, the hardware should be careful about while handling the interrupts. So this is one type of event that can cause operating system to come into picture and execute, right? Whenever a device interrupt arrives to the CPU, CPU stops the current running application and executes what? Execute interrupt handler, which is a piece of software, which is a function that is part of the kernel implemented inside the operating system, implemented by the operating system, usually by the device drivers, okay? So device drivers are part of the operating system as well. So this function is executed. So in this way, that means we can say operating system is now executing in the CPU. A function of that is executing in the CPU. Before that, application program was running using the CPU, and when interrupt happens, then what happens? The operating system routine handling the interrupt is executing in the CPU and doing the job required whenever the interrupt, when the interrupt arrives, okay? So this is one way or one event that causes the OS to execute. Another event that causes the OS to execute is this. As we have said earlier, the OS is loaded into memory in the beginning and stays there all the time, but it is not all the time executing in the CPU. It is executing in the CPU whenever required. And it is required to execute in CPU, for example, when an interrupt, hardware interrupt arrives. The other thing that can cause the OS to execute in the CPU is the traps. What is that? A trap is a software-generated interrupt caused either by an error or a user request. So, for example, when the currently running application okay, tries to divide by 0, what happens? It cannot divide by 0, right? The hardware detects that and it stops the application. And it calls, the hardware automatically starts running a special operating system routine to handle that. This is called trap, okay, an exception. So this is generated by the currently running application because it tries to do something illegal, okay? The hardware detects that and stops the application and gives now the CPU to some operating system routine to handle that exception. Again, that routine is now running in the CPU. The application is no longer running and handling that exception. For example, that handling may involve writing something to the screen. Like, for example, you are trying to divide by 0 and so on, okay? So again, operating system is executed in the CPU. This is another event that can cause operating system routines to execute in the CPU, exceptions. And the third one is the input-output requests by the applications or system requests. So as I said, the applications, whenever they would like to do the I/O, they cannot do the I/O by themselves. They have to call an operating system routine to do that. So if an application would like to do I/O, then it calls the services of the OS. And this is another event that can cause operating system routines to be executed in the CPU to do the task, to do the I/O and so on, okay? So this is another event, and this is called trap, okay? So it's a software interrupt. So it is generated by the software or application running in the CPU. A system call is made to get a service from the OS, and therefore the currently running application is interrupted, stopped, okay? And a special machine instruction, which is called trap, is run, okay, to start executing kernel code in the CPU, all right, after suspending the application. And this is called trap. All right, so as a result, we have the operating system code to execute whenever, for example, devices give interrupt to the CPU, or whenever applications require some service from the operating system, and for that purpose they trap, okay? Or whenever an application running in the CPU tries to do something illegal, okay? These are called exceptions. Whenever exceptions happens, whenever traps happens, or hardware interrupts happens, then operating system routines, operating system code that you have loaded initially to memory starts running in the CPU. Otherwise, the CPU is either idle or is used by the application programs. The Java program that you are writing, for example, that is doing number crunching, doing heavy computing and so on, okay? Doing lots of arithmetic, okay? Then it can run in the CPU without requiring the I/O, without doing some I/O. And when it needs to do I/O, then it calls the operating service routine to do that. This is called trap, and that operating systems routine is run in the CPU to do the I/O, okay? Is it clear? Therefore, we say that the operating system is interrupt-driven. So it is loaded all the time in the memory, but it is run in the CPU whenever interrupts happen. Software or hardware interrupts, okay? So this is enough for this hour, and we will continue from here in the next lecture, okay, after the break, okay?